Welcome to Tell Me More Stories Told As podcast.
It's great to be diving into another story.
Absolutely. Get ready, folks, because today we're launching into an adventure, a real historical blast-off exploring the captivating story of rockets.
Yeah, forget the dry textbook stuff. We're talking about the surprising journey, the twists and turns of these incredible machines.
Exactly. Think of this as your personal deep dive. We'll look at, where they came from, these ancient fiery beginnings, right up to their massive role in space exploration and, well, everything else.
That's the plan. We'll unpack what makes them tick, uncover some unexpected developments, and really highlight the ingenious thinking behind it all.
We've gathered a whole load of fascinating info to guide us. We want to reveal the core story, the essentials you need to know without getting bogged down. Ready to ignite this?
Let's do it. Where do we start? Ancient China.
You got it. Way back. 13th century China.
Yeah.
Song Dynasty.
Right. So picture this. They're figuring out gunpowder, and they start harnessing its power to create, well, the first real rockets.
Not just firecrackers, though.
No. I mean, they were developing early forms of multiple rocket launchers.
Mm-hmm.
Think about that. It's like a vision of modern artillery, but centuries early.
That's incredible. And this tech didn't just stay put in China, did it?
Nope. The Mongol invasions, interestingly, kind of spread it around westward, to the Middle East, and then eventually into Europe around the mid-13th century.
Wow. So conflict actually helped spread the technology.
Inadvertently, yes. And we even have records like around 1245, the Song Navy used rockets in a military exercise. Quite a display, I imagine.
A very different kind of naval power. Now, I read something about a ground rat. Sounds odd.
Yes, that's a fun little anecdote from 1264. Apparently, a type of firework, this ground rat, you can picture it, right, skittering around, sparking it, managed to scare the Empress Mother Gongsheng pretty badly during a feast.
Oh, dear. Shows how unpredictable they were back then.
Exactly.
Yeah.
A little glimpse into the less controlled side of early pyrotechnics. But they were learning refining things.
Which brings us to the Wulongjing, the Fire Drake Manual. Even the name sounds epic.
It really does. And it's a key text. Mid-14th century, written by an artillery officer named Zhao Yu. It describes what many believe is the first known multi-stage rocket.
Multi-stage back then.
Yep. Called the Fire Dragon issuing from the water. Sounds dramatic, doesn't it? The thinking is the Chinese Navy might have used it. So even that early, they were grappling with the idea of stages for more power and range.
Fire-breathing water dragons.
Yeah.
Quite a leap to the Saturn V. But these weren't just for show, right? Military uses were obvious.
Oh, absolutely. Medieval and early modern armies saw the potential pretty quickly. Incendiary weapons, especially for sieges.
Yeah.
Loving fire over walls,
Makes sense. And people were actually writing down recipes for this stuff.
Yes, definitely. There's Hassan al-Rama around 1270 to 1280. His book on military arts had, I think, 107 gunpowder recipes, and 22 of them were specifically for rockets.
22. So it was becoming quite specialized.
It suggests a real level of understanding, yeah.
Yeah.
Design, construction, specific uses.
So the know-how is being documented. What about Europe? Were they catching on?
They were. Roger Bacon, writing around 1267, mentions firecrackers being used in different places, so the idea was circulating. A bit later, the Liber Ignium had instructions for similar devices based on accounts reaching Europe.
Okay, so the knowledge is spreading. And then you get figures like Conrad Kaiser and Giovanni Fontana adding their own spin.
Exactly. Kaiser, around 1405, includes rockets in his military book Bella Fortis, still relevant for war.
Great.
And Fontana, around 1420, he was quite imaginative, designed rocket-propelled animal figures.
Rocket-powered animals? Seriously, like what, pigeons?
Well, the specifics are a bit hazy, but imagine wooden birds or something propelled by rockets, maybe for entertainment, maybe battlefield psychology, who knows?
Definitely unique. So different from the precision engineering we think of now. Speaking of words, where did rocket come from? It doesn't sound very explosive.
No, it's quite mundane, actually. Comes from the Italian rochetta. It means bobbin or little spindle.
Yeah, bobbin. Like for thread.
Exactly. Because the early forms kind of resembled the bobbins used on spinning wheels. Simple shape similarity. The name stuck and spread into German and English by the early 1600s.
From sewing supplies to space travel. History's funny. Okay, let's jump forward. The Mysorean rockets in India, these seem like a big deal.
Oh, they were. Late 18th century Kingdom of Mysore under Hyder Ali. These were the first really successful iron-cased rockets.
Iron instead of paper or bamboo.
Right. And that simple change was revolutionary. Iron casings could handle much higher internal pressures. That meant more thrust, much greater range. They were very effective against the British East India Company forces.
So effective, the British basically copied them.
Pretty much, yeah.
Yeah.
Sir William Congreve based his own rocket design directly on the Mysorean tech, developed around 1804.
The Congreve rocket.
That's the one. Used compressed powder, saw action in the Napoleonic Wars. And fun fact, when Francis Scott Key wrote The Rocket's Red Glare during the War of 1812 at Fort McHenry.
He was talking about Congreve rockets.
Exactly. Those were the rockets lighting up the sky.
Wow. That adds a whole new layer to the Star-Spangled Banner. And this leap in range was significant.
Hugely significant. Went from maybe 100 yards effective range to like 2,000 yards. A game changer on the battlefield.
That kind of jump must have spurred more serious study, too.
It did. You start seeing the first mathematical analyses of rocket propulsion. William Moore published something in 1813. Then guys like Zasyadko in Russia designing launching platforms around 1815. And later improvements by Hale and Boxer focused on making them more accurate.
Okay, so the military side is really pushing things forward. But when does the dream shift? Looking up. Spaceflight.
Well, the absolute earliest flicker of that idea comes surprisingly early. A Scottish writer and clergyman, William Leitch.
Leitch. Never heard of him in this context.
Not as famous as the later names, but back in 1861 he proposed using rockets for human spaceflight in an essay called A Journey Through Space. He saw them not just as weapons, but as, well, vehicles for other worlds.
1861. That's way before the pioneers we usually think of.
It is. Then independently, you have Konstantin Tsiolkovsky in Russia.
Ah, Tsiolkovsky. Now there's a foundational name.
Absolutely. He published his major work on spaceflight theory using rockets in 1903. He didn't just dream it. He developed the core theoretical principles. Multi-stage rockets, liquid propellants, he laid so much groundwork. A true father of astronautics.
So while armies are perfecting battlefield rockets, these guys are already aiming for the stars, conceptually at least. The early 20th century must have been buzzing with these ideas.
It really was. Things started accelerating. Even during World War I, the British Royal Flying Corps was messing around with a guided rocket concept.
Guided in WWI.
Yeah, under Archibald Lowe. They patented improvements in rockets in 1918, kept secret till 23. Talking about electrical steering, even wired and wireless guidance. Pretty advanced thinking for the time.
Amazing. And then we get to the big names of early modern rocketry, right? Goddard, Oberth.
The crucial figures who started turning theory into, well, actual hardware. Robert Goddard, the American professor. His 1920 paper, A Method of Reaching Extreme Altitudes, was huge. Laid out improvements, really pushed the idea of liquid propellants.
And Oberth.
Hermann Oberth, German physicist. His 1923 book, The Rocket into Planetary Space. It captured the public imagination, but also had serious math and engineering behind it. Really fueled the dream for a lot of people.
And then Goddard actually did it in 1926, the first liquid fuel rocket launch. That feels like the real starting pistol for modern rocketry.
Many see it that way, yes.
Yeah.
March 1926. It wasn't just liquid fuel, though. His rocket used a supersonic nozzle, a de Laval nozzle.
Okay, what's special about that?
It dramatically increases thrust and efficiency. It shapes the exhaust flow perfectly to convert pressure into speed. That, plus the controllability and higher energy of liquid fuels compared to gunpowder. It was a massive leap forward.
Liquid fuel and supersonic nozzles, the core combo. What about elsewhere? The Soviets?
Right, important work happening there, too. The Gas Dynamics Laboratory, starting in 1921, focused heavily on solid propellant rockets.
Solids, okay. Less complex in some ways.
Can be, yeah. They had their first successful launch in 1928, reached about 1,300 meters. And these solid rockets found interesting uses quickly. Like, in 1931, the first use of rockets for jet-assisted takeoff for aircraft.
JSO. Helping heavy planes get off the ground.
Exactly. And crucially, these Soviet solid rocket designs, they were the direct ancestors of the Katyusha rocket launcher.
The Katyusha. Stalin's organ. Famous in World War II.
The very same. So you see parallel tracks, Goddard pushing liquid fuel in the U.S., the Soviets making big strides with solids, both paths proving incredibly important.
It's fascinating how these different approaches developed. Okay, folks, we're about halfway through this incredible journey. If you're enjoying this deep dive into the surprising history and science of rockets, do us a favor and hit that subscribe button for Tell Me More Stories Told as podcast.
Yeah, don't miss out. We still got loads to cover, including how Hollywood got involved, the shadow of World War II, and the race to space itself.
Definitely stick around. Right, so back to the story. The 20s and 30s, popular culture is getting interested too. You mentioned Fritz Lang's film Woman in the Moon.
Oh, absolutely. 1929. A German science fiction film but incredibly influential and surprisingly realistic for its time.
What made it so realistic?
Well, it showed a multi-stage rocket, which was cutting-edge thinking. It had the concept of a launch pad moving the rocket into place. And it's credited with inventing the dramatic pre-launch countdown.
The Countdown, from a 1929 sci-fi film.
That's what film historians argue, yeah. It really shaped how people visualize space travel.
Was it based on any actual science?
Yes, Lang was inspired by Herman Oberth's book, and Oberth himself was the scientific advisor on the film.
Ah, so Oberth consulted on it. That explains the realism.
It does. So much so, apparently, that when the Nazis came to power later, they banned the film. They were worried it was too accurate and might give away secrets about their own developing rocket program, the V-2.
Wow. Life imitating art, or maybe art getting a bit too close to secret military tech. And speaking of the V-2, that's a huge and dark chapter.
It is. Germany starts mass-producing the V-2 in 1943. Peenemünde Research Center, Wernher von Braun leading the technical side. It was a technological leap, no question.
The first object to reach space, right?
Technically, yes. It crossed the Kármán line, the edge of space, on a test flight in 1944. An incredible achievement from an engineering perspective.
But built under horrific circumstances.
Absolutely essential to remember that. The V-2 program used vast resources and relied heavily on slave labor from concentration camps. Thousands died building it. A technological marvel born from atrocity.
A very sobering point. Now, during the war, rockets weren't just the V-2, were they? Aircraft used them too.
That's right. We mentioned JATO jet-assisted takeoff. Rockets gave planes that extra boost. There were even rocket-powered interceptors like the German Me-163 Comet.
A plane powered only by a rocket. It must have been terrifyingly fast.
And had very short endurance. On the Allied side, the focus was more on simpler, unguided, solid rockets, like the Katyusha for massive barrages and the American Bazooka, a shoulder-fired anti-tank rocket.
So World War II massively accelerated rocket tech, mainly for weapons. What happens when the war ends? The space age is looming.
A lot of that German expertise gets redistributed. Operation Paperclip brings Wernher von Braun and many of his team to the U.S.
Right, to work for the American military and space program.
Exactly. Their knowledge was crucial. Meanwhile, both the U.S. and the Soviets kept using rockets for research high-altitude atmospheric stuff. Think of the Bell X-1 breaking the sound barrier in '47. That was rocket-powered.
And the Soviets had their own experts, like Korolev.
Sergei Korolev, yes.
Oh.
A brilliant engineer who led the Soviet program, often under immense political pressure. He'd survived Stalin's purges.
And then the Cold War kicks in and rockets become central.
Utterly central. ICBMs, intercontinental ballistic missiles. The nuclear threat meant massive investment in powerful, reliable rockets on both sides. That fierce competition, ironically, drove the technology needed for space exploration at an incredible pace.
The space race?
Exactly. The 1960s saw just explosive growth in rocket capability. Mercury, Gemini, Apollo, all built on that rapidly evolving tech, culminating, of course, in 1969.
The moon landing, powered by the Saturn V.
The Saturn V, still the most powerful rocket ever successfully flown. A true giant, born from that intense period of development, from ancient Chinese fire arrows to that beast. It's quite a story.
Absolutely breathtaking. Now let's broaden out a bit. Rockets today, they're not all giant moon machines, are they?
Oh, not at all. The variety is huge.
Yeah.
You've got tiny model rockets for hobbyists, which are great for getting kids into science. Fireworks, of course. Then military missiles of all shapes and sizes.
And for space?
Launch vehicles, sure, like the Falcon 9 or Ariane, but also sounding rockets for atmospheric research, probes going to other planets, and then weirder stuff. Rocket cars, rocket bikes, even rocket-powered jetpacks, though those are mostly experimental.
Rocket sleds too, right, for testing things really fast.
Yep, incredibly fast. Testing components, ejection seats, things like that.
Oh.
Also rocket torpedoes, escape systems for astronauts, ejection seats for pilots. The applications are incredibly diverse.
So what are the absolute basics? What does every rocket need?
At its simplest, propellant, the stuff that throws out, a container for the propellant to tank, and a nozzle to direct the exhaust. That's the bare minimum.
Okay, but real rockets are more complex.
Right. You add engines, stabilization systems, could be fins, could be smaller vernier engines, or thrust vectoring where the main nozzle itself can gimbal or swivel to steer, plus the structure holding it all together.
And nose cones.
For atmospheric flight, yeah. Aerodynamic fairings like nose cones are vital to cut down drag at high speeds. Then you can add wings, parachutes for recovery, landing gear, guidance systems. Depends on the mission.
Makes sense. We talked about liquid and solid propellants. What are the main engine types?
Those powerful rockets are chemical rockets. They work by burning a fuel with an oxidizer. This combustion creates hot, high-pressure gas.
Fuel and oxidizer, like gasoline and air in a car, but way more intense.
Sort of, but rockets usually carry their own oxidizer since there's no air in space. And so liquid hydrogen fuel with liquid oxygen oxidizer or kerosene fuel with liquid oxygen. Solids have the fuel and oxidizer mixed together in a solid block.
Are there other kinds besides chemical?
Yeah. Monopropellants decompose using a catalyst simpler, good for small thrusters. Hypergolic propellants ignite just on contact, reliable, often used in spacecraft. And then there are concepts like nuclear thermal rockets or solar thermal rockets, where you heat a propellant, like hydrogen, with an external source instead of burning it, or even just expelling pressurized gas for very small adjustments.
Lots of ways to generate thrust. Now, you mentioned something earlier, a fun fact moment perhaps, the pendulum rocket fallacy.
Ah, yes. A great little story about Robert Goddard, actually. His very first liquid fuel rocket, the one he launched in 1926.
The big breakthrough one.
That's the one. He designed it with the engine and nozzle at the top and the fuel tanks below it.
Upside down, basically. Why?
His thinking was it would be inherently stable, like a pendulum hanging down. The heavy tanks at the bottom would keep it upright, he figured. Seems logical, right?
Kind of does, yeah, like a weighted dart.
Exactly.
Right.
But nope. When he launched it, it went up a little bit, then immediately veered off course and crashed just 184 feet away.
Oh, dear. So the pendulum idea didn't work.
Not at all. It proved that putting the engine at the top doesn't make a rocket any more stable. The thrust pushes along the rocket's axis, regardless of where the weight is concentrated. Stability comes from fins or active guidance, not from hanging the tanks underneath. A classic early misconception, beautifully disproven by experiment.
The pendulum rocket fallacy. I like it. A good reminder that intuition isn't always right in physics. Okay, so beyond the big military and space uses, where else do rockets pop up?
Well, science and research is a big one. We mentioned sounding rockets carrying instruments high up to study the atmosphere, ionosphere, aurora. Great data gathering. And those rocket sleds for high-speed testing are crucial for aerospace development.
Hitting Mach 8.5 on rails. Insane. What about, like, rescue stuff?
Yes, actually. There are systems that use rockets to fire lines out to ships in distress, to set up rescue connections like a breaches buoy. Emergency flares are often rocket-propelled for height and visibility.
Astronaut escape systems.
Crucial safety tech. Launch escape systems pull the capsule away from a failing booster. Ejection seats for pilots. They rely on powerful, fast-acting, solid rockets. And they have saved lives, notably the Soyuz T-10 crew in 1983, whose rocket caught fire on the pad just before launch. The escape system yanked them clear.
Incredible. Life-saving rockets. And on the lighter side, hobbies.
Oh yeah. Model rocketry is huge. Safe, educational, inspires future engineers. Water rockets are fun physics demos. Then you get into amateur rocketry, which can get pretty serious, even reaching space altitude sometimes. And the more fringe stuff, jetpacks, rocket cars. Mostly for show or records, but still using rocket principles.
So from saving lives to weekend hobbies. Very versatile. Let's talk about flight itself. How does a typical launch work? Getting into orbit.
Usually starts vertical, right? Punch through the thickest air.
Yeah.
Then it performs a gravity turn.
Gravity turn.
Yeah, gradually pitches over, letting gravity help bend the trajectory towards horizontal. More efficient than trying to fight gravity straight up and then turn. Keep burning, gaining speed and altitude until you hit orbital velocity at the right height. Then, engine cutoff, and you're coasting in orbit.
And staging is key for that, dropping bits off.
Essential for almost all orbital launches currently. You shed the weight of empty tanks and engines from the lower stages. Improves the mass ratio for the upper stages, lets them add more speed. Without staging, getting enough delta V, enough velocity change for orbit with a decent payload is extremely difficult with current chemical rockets.
Single stage to orbit is still the dream, though.
It is, but a very tough engineering challenge. Maybe with air-breathing engines for the atmospheric part, or future propulsion, but not with pure rockets yet.
And what's a dogleg maneuver? Sounds like something you wouldn't want.
Usually, yeah. It's a deliberate turn during ascent, not part of the gravity turn. Used maybe to avoid flying over populated areas or to hit a specific orbital inclination from a launch site that isn't ideally located. But it costs performance, uses extra fuel, reduces payload, so you avoid it if you can.
Right. Okay, let's talk about the sheer power. The noise of a launch is immense. What's actually making that sound?
It's the violence of the exhaust. Supersonic gases hitting the relatively still air creates massive shock waves. Acoustic energy. The bigger the rocket, the faster the exhaust, the louder the noise. We're talking levels like 180 decibels for the space shuttle near the pad. Instantly deafening, potentially damaging.
180 decibels. How do they even manage that? Protects the rocket itself, the pad.
Water. Lots and lots of water. Sound suppression systems spray hundreds of thousands of gallons of water per minute onto the launch mount and into the flame trench below the rocket.
Water absorbs the sound.
Absorbs a lot of the acoustic energy, yeah. Turns it into steam. It also cools things down. Without it, the sound waves could literally shake the rocket and its payload apart. The noise is most intense right near the ground as the exhaust plume expands.
Incredible engineering just to handle the side effects. Let's get down to the physics, nuts and bolts. How does burning fuel become thrust?
Okay, combustion in the chamber creates super hot, high-pressure gas. The nozzle's job is to accelerate that gas. It narrows, converges, then widens, diverges. This shape converts the random thermal energy and high pressure into directed, high-velocity motion out the back.
So the nozzle is key.
Absolutely critical. It's all about Newton's third law. You throw mass, the exhaust gas, out backward at high speed. The rocket gets an equal push forward. That push is thrust. It's fundamentally about managing pressure differences and directing momentum.
Got it. And in flight, what forces are acting on the rocket?
Four main ones,
Yeah.
typically. Thrust from the engine, pushing it forward. Gravity, pulling it down or towards whatever large body is nearby. Drag, air resistance if it's in an atmosphere. And lift if it has wings or body shape that generates it, mostly relevant for rocket planes. In space, it's mainly thrust and gravity.
We talked about the gravity turn using gravity. How do they minimize drag?
Shape is key. Streamlined, pointy nose cones, smooth surfaces, keep the angle of attack low fly, mostly parallel to the airflow, and just getting out of the thick lower atmosphere as quickly as possible helps. There's a point called max Q,
Max Q.
maximum dynamic pressure. It's where the combination of air density, decreasing with altitude, and the rocket's speed, increasing, creates the biggest aerodynamic stress on the vehicle structure. It has to be built tough enough to handle that moment.
Okay. We keep saying thrust. How is it actually, calculated?
Net thrust depends on two main things. How fast you're throwing mass out, mass flow rate of propellant, and how
Yep.
fast that mass is going, effective exhaust velocity. More mass per second or higher exhaust speed equals more thrust. Controlling the propellant flow lets you throttle the engine.
And specific impulse. That sounds important for efficiency.
It is. Specific impulse, often written as ISP, is basically the rocket engine's fuel efficiency. It measures how much thrust you get for the amount of propellant used per unit of time. Higher ISP means more bang for your buck, propellant-wise. It's directly related to that effective exhaust velocity. Higher exhaust velocity means higher specific impulse.
So higher ISP is better. And delta V. That's like the rocket's total potential.
Exactly. Delta V is the total change in velocity a rocket can achieve. It's calculated using the Tsiolkovsky rocket equation, which connects delta V to the specific impulse or exhaust velocity, and the rocket's mass ratio.
Mass ratio.
Yeah, the ratio of the rocket's starting mass, full of fuel, to its ending mass, empty. The more propellant you carry relative to the dry structure, the higher the mass ratio and the more delta you can get. Delta V is like the currency for space maneuvers. You need delta V to get to orbit, change orbit, go to the moon, etc.
Okay, so ISP tells you fuel efficiency, mass ratio tells you how much of your rocket is fuel, and delta V tells you the total speed change you can achieve.
That's a good summary. And that's why staging is so important. Dropping empty tanks massively improves the mass ratio of the stages that are left, letting them achieve much higher delta V than a single stage ever could.
It all fits together. The acceleration must be incredible, too.
Oh yeah, rockets have extremely high thrust-to-weight ratios compared to other engines. That's why they can lift straight up. Acceleration actually increases during a burn because the thrust stays roughly constant while the rocket's mass decreases as it burns fuel. The G-forces can get pretty intense, especially on something like a launch escape system, maybe 20 Gs.
Wow. Okay, one last area, efficiency and cost. Are rockets efficient?
Depends how you measure it. In terms of converting chemical energy in the propellant to kinetic energy of the exhaust, modern engines can be pretty good, maybe up to 70% efficient.
Yeah.
But overall propulsive efficiency, how much of that energy actually goes into speeding up the rocket versus just blasting hot gas out the back, is quite low at low speeds. Rockets are terrible for, normal airplanes. They're only really efficient at very high speeds.
And there's the Oberth effect, too.
Right. That's a fascinating one. Basically, using your rocket engine applying delta V when you're already moving fast, like deep in a gravity well close to a planet, gives you a bigger change in orbital energy than applying the same delta V when you're moving slowly. It's why major burns for interplanetary travel are often done close to Earth or other planets, get more energy boost for the same fuel burn.
So timing your burns matters a lot. What about safety and cost? Rockets seem risky and expensive.
They are inherently energetic systems, so yes, failures can be catastrophic. Reliability depends hugely on engineering quality and testing. Historically, spaceflight has been risky. Costs are high too. Propellant itself isn't that expensive for big rockets, but the hardware, the engines, tanks, guidance systems is incredibly complex and costly to design, build, and test. High performance demands high cost.
Is that changing at all? Reusability.
That's the big push now, yeah. Reusable rockets like SpaceX's Falcon 9 aim to drastically cut costs by recovering and reflying the most expensive parts, especially the first stage boosters. Mass production could also help, and the increased private competition in the launch market since the 2010s is definitely putting downward pressure on prices.
It's a constantly evolving field then.
Absolutely, always pushing the boundaries of performance, cost, and reliability.
Well, we have covered an immense amount today, from, those first fiery arrows in China to the physics of Delta V and the economics of modern launch providers. It's just an incredible story.
It really is. Centuries of human ingenuity driven by warfare, curiosity, and that fundamental desire to explore what's out there.
So as you've heard, the story of rockets is this dynamic, sprawling journey, from simple gunpowder devices to these unbelievably complex machines that carry us quite literally to other worlds. And let's not forget that wonderful pendulum rocket fallacy, a great reminder that even geniuses learn by trial and, well, error.
We really hope this deep dive has maybe sparked some curiosity, given you a clearer picture of rocket science and its amazing history.
Definitely. So, what other incredible stories are hiding inside the tech that shapes our lives? Keep exploring, keep asking questions, and please join us again next time on Tell Me More Stories Told Us podcast, when we'll unpack another fascinating topic.
Maybe you'll think about the challenges of making space travel routine or the ethical questions that come with powerful technologies. There's always more to explore.
Until then, keep looking up.